right. Good morning, everyone. Are there any questions? Okay, so what we're going to do is continue on where we left off at. so, um, we're going to be dealing with today, um, dealing with the double integrals. Oops. Over a general region. Okay. All right, so one of the things that we're going to do is go back and revisit Fubini's theorem and just make it a little bit stronger. Okay, so we can have our region, okay, define where x is bounded between a and b, and then we can say that y is bounded between two different functions, so g sub 1 of x and g sub 2 of x. Okay? So if we want to do the double integral over the region of f of x, y, dA, we're allowed to write this as the integral from a to b, then the integral from g sub 1 of x to g sub 2 of x of f of x, y, dy, dx. Okay. Now, we have to be careful with this in that when we are dealing with this, okay, we do need to make sure that the numbers are on the outside, okay? We don't want them on the inside because then we won't be basically evaluating the double integral, okay? All right, now in your notes, it talks about some of the formulas and things in there, and you guys can take a look at those and everything. Okay, so what I want to do is to jump down into the examples and let's talk about those. All right, so the first example we're going to take a look at is the following. So we've got the double integral from 0 to pi, and then integral from 0 to sine of x of y dy dx. Okay. So the first thing you want us to do is to sketch the region of integration. Okay. So if we take a look at sketching the region, so basically, all right, this here is dealing with x values, this here is dealing with y values. So let's deal with the x values first. So as far as x is concerned, we're starting at 0, we're ending at pi. Okay? As far as y is concerned, we're starting at 0, and then we're ending with the sine of x. So what we're going to do is to graph the function. We're going to graph sine of x between 0 and pi. Well, at 0, we know it's 0. At pi over 2, we know we're going to be at 1. We're going to be at its max. And back at pi, we're going to be at 0. So we're going to get this, okay? And this is the region of integration that we're dealing with. Right. Any questions there? Okay, so now what we're going to do is to evaluate the integral. All right, so if we do that, we're going to have the integral from 0 to pi. Antiderivative of y is going to be 1/2 y squared, and we're going to evaluate from 0 to sine of x, and we're going to do dx. The nice thing is that if we plug in 0, we're going to get 0, so we're going to kind of ignore that. So we're going to end up with the integral from 0 to pi of 1/2 sine squared x dx. Okay, so in order to integrate this, we're going to use our power reduction identity. So when we do the transformation, we're going to end up with the integral from 0 to pi of 1/4 times. We're going to have 1 minus the cosine of 2x dx. And now we're ready to integrate. So if we integrate this, we're going to have 1/4 times. We're going to end up with x minus 1/2 sine 2x. We're going to evaluate that from 0 to pi. Okay. Now, if we plug in 0, we're going to get 0, so we don't need to worry about that. So we're going to have 1/4 times. If we plug in pi, the first term is going to be pi. The second term is going to be 0. So we're going to end up with pi over 4. Any questions?
For the first evaluation, would it be negative 1/2 sine squared x instead of subtracting?
No, we do top minus bottom.
Oh yeah, that's true. Never mind.
No problem. Any other questions? Okay, so let's look at our next example. All right, so our next example, we've got the integral from 0 to 1. Then we've got the integral from 0 to the square root of 1 minus s squared. We got 8t dt ds. All right, so again, first thing we're going to do is to sketch. So if we sketch, we're going to say this is the s-axis, this is the t-axis. So along S, we're going to go from 0 to 1. And then as far as t is concerned, we're going to start off at 0, and then we're going to go up to the square root of 1 minus s squared. So what we're going to do is just plug in the values from 0 to 1. Okay? So if we plug 0 into this, what will we get? We get 1. And if we plug 1 in, what do we get? 0. Okay, so basically, this is what we're going to get as far as the piece is concerned. Okay. Any questions? All right, so let's do the integral. So we're going to end up with the integral from 0 to 1. All right, so what's the antiderivative of 8t? Okay, so we're going to have 4t squared. We're going to evaluate it from 0 to the square root of 1 minus s squared. And then we're going to integrate in respect to s. All right. So again, the nice thing with this, since the lower limit is 0, this is going to be 0, so we don't really have to worry about this. So we're going to end up with the integral from 0 to 1 of 4 times. If we square this, we're just going to end up with 1 minus s squared. ds. Now I'm going to go ahead and distribute through. So it's going to be the integral from 0 to 1 of 4 minus 4s squared ds. So if I find the antiderivative, what will I get?
Of 4x minus 4 over 3 s to the power 3.
Okay. So 4s minus 4/3 s cubed, and we're going to evaluate from 0 to 1. Again, if we plug in 0, we're going to get 0, so we don't have to worry about the upper limit. It's just the lower limit. It's just the upper limit that we need to evaluate at. So if we do that, we're going to get 4 minus 4/3, and that's going to give us what?
8 over 3.
8/3, and that would be our answer. Any questions?
Can you explain again the graphing part?
As far as the graphing is concerned, so S is the x-axis, T is going to be the y-axis. So S is going from 0 to 1. So basically all I'm doing is plugging in the values from 0 to 1 into the square root of 1 minus s squared.
Oh, I see. All right. Thank you.
Mm-hmm. Any other questions? Okay, so let's look at our next example. It's the next set. All right, so in the next set of examples, we're going to sketch the region of integration and then write an equivalent double integral with the order of integration reversed. Okay, so for the first one, we're going to have the integral from 0 to 2, and then the integral from y minus 2 to 0 of dx dy. Okay, so what we're going to start off with first is we're going to graph the region. Okay, so here's x, here's y. Now, since y is second, that means y is running from 0 to 2. So starting off at 0, then 1, 2 is where we're going to end. Now, for the other piece, we're running from y minus 2 to 0. So basically what we're going to do is to put in the values of y to get the values of x. Okay, and let me redraw my graph a little differently. I need more room on the left than what I put. Okay, so if I start off with y is 0, what is x going to be? And just keep in mind that these are x is equal, okay? So x is going to be -2, so we're going to go 2 to the left. There's our point. All right, if I plug in 1 for y, x is going to be what? -1. And if I plug in 2 for y, x is going to be what? It's going to be 0. Okay, so we're going to end up with this here. Okay, so now what I want to do is to write an equivalent. So I'm going to do the double integral, but this time I want y first, then x second. Okay, so I'm going to look at the graph to help me out with this. Okay, so since x is second, I need number values. So based on the graph, what values will I use for x? Yes, -2 to 0. Okay. Now, based on the inner part, we're dealing with y. Okay. And so keep in mind the way this is going to work for the y starting here, then we're going to go up to here. Now, when we're doing this, we're going to be following along this. So y is going to start off at 0. Then it's going to go up to, now it's not going to be a number. So what we're going to do is take this equation and solve for y. So what is y going to be equal to? And that's going to be the upper limit. Any questions? All right, let's take a look at the next example. So in the next example, we have the integral from 0 to 2, then the integral from 0 to 4 minus y squared, and we have y dx dy. Okay. So again, what we're going to do here is to write what we're going to do is to draw a picture of what we're dealing with. So if I take a look at this, on the outside is y, so y is running from 0 up to 2. So now what we're going to do is to deal with x. Now again, just as I said last time, this is basically x is equal to 0. This is x is equal to 4 minus y squared. So when y is 0, what is x going to be?
4.
It's going to be 4. All right. When y is 1, what's x? Okay, it's going to be 3. And then when y is 2, what's x?
0.
Okay, we're going to get 0. So if we connect these, this is what we're going to have. Okay. So when we write the equivalent, so we're going to do our double integral. The function's still going to stay. It still says as y, but we're going to change the order. So we're going to do dy, then dx. Okay. Now, based on the graph, what are the values for x? Based on the graph, what are the values for x? 0 to 4. Okay. Now let's deal with the values for y. Okay, so keep in mind what's happening here is that when you start, you're starting down here, and then you're working your way up along the curve. So the lower y value is going to be what? Our lower y value is going to be what? It's going to be 0. Okay, now to find our upper y value, basically what we're going to do is we're going to set the equation. So what we're going to do is to solve for y. So if we solve for y, we can add y squared to both sides and subtract x. So what is y going to be equal to? Okay, and be the square root of 4 minus x. Now, keep in mind that technically it would be plus or minus. Okay, technically it would be plus or minus. But we know it's going to be the positive because we are on the positive side of the graph. Okay, so our upper limit here is going to be the square root of 4 minus x. Any questions? Okay, let's look at our next example. So we have the integral from 0 to 2. Then we have the integral from 0 to 4 minus x squared. And we have x e to the 2y over 4 minus y. We're doing dy dx. Okay, so if we take a look at sketching this graph, right? Again, what we want to do is we want to start with the outer portion because it kind of gives us what the values are for that particular variable. So since x is on the outside, x is going from what to what? 0 to 2. So we're going to have 0, 1, and 2. Okay. And then for the other one, keep in mind this is y equals, this is y equals. Okay. So we're going from 0 up to along the curve. Okay. So what we're going to do is just plug in the x values into the curve. So when x is 0, what's y?
4.
4. 1, 2, 3, 4. All right, when x is 1, what's y?
3.
And then when x is 2, what's y?
0.
Okay, so here's what we're going to get. Any questions there? So now let's write the equivalent. So we're going to have our double integral. We're going to keep the function as is. Now we're going to switch to order of integration. Okay, so let's start on the outside. It's y. So based on the graph, what are your values on y?
0 to 4.
So 0 to 4 goes here. Now, on the inside, we're going to deal with x. Okay, so if you think about how x is running, x is starting here and going over. So the first x value is going to be what?
0.
It's going to be 0. Now, the second x value actually is going to be the curve. It's going to be the curve. So what we're going to do is say, okay, we know that y is equal to 4 minus x squared. If we solve for x, what's x going to be equal to?
Square root of 4 minus y.
Okay, square root of 4 minus y. And that's going to be our upper limit. Any questions?
So we only have to, I mean, we only have to worry about the limit, right? Like, I mean, integration.
Yes. Yes.
Okay.
All right. Okay, so let's look at one more. So the last one we have is this. So we've got the integral from 0 to 8. We've got the integral from the cube root of x to 2 of dy dx over y squared, y to the fourth plus 1. Okay, so here's the reason why we need to understand how to do the changing of the variable. I mean, changing of the limits of integration. Okay, in this problem, okay, most people look at this problem and it's like, I may be able to integrate this using partial fractions or something like that. Okay, and in reality, this problem is a inverse trig. Okay, but we can't do it. Okay, because we don't have the u sub, the proper u sub in order to do this. So if we switch the limits of integration around, then we would be able to do this. Okay, so if we switch the limits of integration around and we look at 1 over y to the 4 plus 1 and do dx first, then dy, okay, by doing this, it allows us to pull in the u sub so I can integrate in respect to y. Okay, but now what we need to do is to figure out, well, what would our limits of integration be? So we're going to look at the original to help us out. So we know that since x is second, we're going from 0 to 8. Y is first, so we're going from y equals the cube root of x to 2. Okay, so basically if we plug in the values of x, we're going to get to the upper limit. So when x is 0, we get 0. When x is 8, we're going to get 2. So this is what we're dealing with here. Okay. So now, switching the limits around, so we want y on the outside. So based on the figure, what are our values for y?
0 to 2.
Okay, it's going to be from 0 to 2. And then on the inside, it's x. So x is running from here to here. But keep in mind, x is starting here and it's following along the curve. Okay, now the curve is defined as y equals the cube root of x. Okay, so if I solve for x, that means x is equal to what?
Y cubed.
Y cubed. So the lower value of x is 0, whereas the upper is y cubed. Okay? And I said this is an inverse trig. It's not an inverse trig. It's going to end up being a law of partial fractions. You can do partial fractions, but it's a nightmare. Okay? So with this, now we're able to do this. So if we were to integrate this, be the integral from 0 to 2. Then, since we're integrating for x, it'll be just x over y to the 4th plus 1, evaluated from 0 to y cubed dy. Because you have to remember that 1 over y to the 4th plus 1 is just a constant as far as x is concerned. Now, if I put the lower limit of 0 in, that makes the expression 0, so we kind of ignore that. So we're going to end up with the integral from 0 to 2. In place of x, we're going to put in y cubed. Now, in order to do this, is a u sub. So my u, which will be y to the 4th plus 1, du will be 4 y cubed dy. So we're missing a 4. Introduce that, bring out a 1/4. So ignore, because that's our du. So we're going to end up with 1/4. 1 over u is natural log, absolute value of y to the 4th plus 1, and evaluate it from 0 to 2. So we're going to have 1/4 times. If we plug in 2, we're going to get natural log of what?
$17.
17. And if we plug in 0, we're going to get the natural log of what?
1.
We get the natural log of 1, which is what?
0.
0. So this would be our answer. So it is important to make sure you understand how to do the reversal of the limits, because, for example, in this problem, in the manner that it was written, we are not able to evaluate it in that form. But if we switch the limits of integration around, we're able to do it. Same thing happens in the previous problem. In this previous problem, if we try to integrate with respect to y first, that's a complete nightmare. But by switching the limits of integration around, we can integrate x easily. Okay, that's just going to be 1/2 x squared. The e to the 2y over 4 minus y is just a constant. Okay, so by reversing the limits of integration, it makes it easier to be able to integrate. Okay. Any questions? Okay, so let's look at our last 2 examples for this section. So the last 2 examples of this section is this: find the volume of the solid that is bounded above by the cylinder z equals x squared and below by the region enclosed by the parabola y equals 2 minus x squared and the line y equals x in the xy plane. Okay, so in order for us to be able to do this, okay, what we're concerned with is the plane below. Okay, the plane below is going to help us be able to determine our limits of integration. Okay, so we're going to be looking at the double integral. Okay, our function in this case is going to be x squared. All right, now we are going to have to figure out, are we going to be integrating in respect to y first or x first? And we don't really know quite off the bat. Okay, so before we put dy dx or dx dy, let's draw the plane below. Okay, so if we're looking at the plane below, we're looking at the y equals 2 minus x squared and y is equal to x. Okay, now considering the way this plane is defined, okay, they're both y equals, it probably going to be best to put y first and then x second. Okay, so let's take a look at the plane. So the first one is a parabola. So 2 units up, and it's going to open down like so. And then we've got y equals x going through 0, 0, and cutting through. Okay, so we are focusing on the bounded region to help us. Okay, we're focusing on the bounded region to help us. So to determine and to make it clear why I put y first, it's the way the functions are defined. Since both functions are defined y equals, why go through the hardship of solving for x? Okay, so just keep them in their present form. All right, so to deal with y, we're going to deal with y first. Okay, keep in mind y is up and down. Okay, so based on the bounded region, the lower limit should be what? Not x. Yes, it's going to be x, and then the upper limit, which is going to be what? Yes, 2 minus x squared. Okay, so the lower limit is going to be the bottom function. The upper limit is going to be the upper function. Okay, now what we're going to do is we need to find the values for x. Well, the easiest way to find the values of x is basically to set the two functions equal to each other and solve. So we're going to have 2 minus x squared is equal to x. Basically, we're going to have that x squared plus x minus 2 is equal to 0. Factors nicely into x plus 2, x minus 1 equals 0. So we get that x is negative 2, x is 1. And that's our limits of integration for x. So we're going from negative 2 to 1. Okay. Any questions there? Okay, so let's deal with evaluating this. So we're going to have the integral from negative 2 to 1. All right, so if we take the antiderivative of this in respect to y, what will we get?
One. Oh, sorry, my bad.
Yes, we're going to get x squared y, and then we're going to evaluate it from x to 2 minus x squared. And then we're going to integrate in respect to x. So really, what we're going to have is the integral from negative 2 to 1 of x squared times, okay, we're going to plug in the upper limit for y, which is going to be 2 minus x squared, minus the lower limit, which is x, dx. Now, to make my life easier, I'm just going to multiply that out. So it becomes the integral from negative 2 to 1 of 2x squared minus x to the fourth minus x cubed dx. Any questions there? Okay, so again, what I'm going to do is I'm going to go to that. I'm going to write this last line on the next page. So I'm going to have the integral from negative 2 to 1 of Again, 2x squared minus x to the fourth minus x cubed dx. So if I take the antiderivative of this, I'm going to end up with 2/3 x cubed minus 1/5 x to the fifth minus 1/4 x to the fourth. Evaluate from -2 to 1. All right. So if I put in 1, I'm going to have 2/3 minus 1/5 minus 1/4 minus. If I plug in -2, I'm going to end up with -16 plus 32 fifths minus, let's see, 16 divided by 4, so we're going to get 4. All right, and basically this is where your trusty calculator comes into play to do this calculation, and we should get 63/20. Any questions? Okay, so next, let's take a look at the last example of this section. Okay, so the last example of this section says this: find the volume of the solid cut from the first quadrant by the surface z equals 4 minus x squared minus y squared. I mean, not y squared, minus y. Okay. So in this example, we're dealing with the first octant. And our equation that we're dealing with is z is equal to 4 minus x squared minus y. Okay. And we're trying to find the volume. So again, we're going to do a double integral. Okay. And our function we know is 4 minus x squared minus y. And then we got to figure out how we're going to do. Are we going to do dy dx or dx dy? Okay. Now, in this problem, what's different about this problem than the previous problem? So what did you know in the not so much the three variables, but more of the fact what did you know in the previous problem but we don't know in this problem?
We knew the enclosed regions in the last problem, and then now we don't.
Right. So basically in the last problem we were told what the bounded region was below. In this one we're not. Okay? So we need to figure that out. All right? So if we want to look for the region below, okay, we need to set a variable equal to 0. What variable do you think we should equal to 0? Yeah, it would be z. Okay, we don't want y because y is in the function. Okay, and we need to make sure that that's one of our limits of that's one of the variables that we're using to integrate in respect of. Okay, so since we're doing a double integral basically tells us that we're working with x and y. If we were doing triple integral, then we will be working with x, y, and z. Okay, as long as we're working in rectangular coordinate system. Okay. All right, so if we let z be 0, basically what we're doing is we're shoving the plane down into the xy plane. So by setting z equals 0, I can rewrite this and say that y is equal to 4 minus x squared. Okay. So I put this 3D figure into a two-dimensional aspect. So if I look at this as two-dimensional, I know this is going to be a parabola opening down, and it's going to look like this. Now, considering the fact that it's in the first octant, okay, considering the fact that it's in the first octant, that means x, y, and z are all what? Are all positive. So with that in mind, we don't need this portion of the graph, nor this portion. Okay, since x, y, and z all have to be positive. Okay, does that make sense, everyone? So this is what we're going to focus on. Okay, now with this equation here, what variable should we do first? What variable should we integrate with respect to first? We should do dy first, and then we're going to do dx second. Okay. Now, since we're doing y first, that means we're looking up and down. Okay. So the lower y value would be what?
0.
Would be 0. The upper would be what?
4 minus a squared.
Right. It will be the function. Okay. Now, based on what I've got circled, now I'm going to deal with x. So, what's going to be our lower x value?
Zero to 2.
Yes, 0 is going to be our lower, 2 is going to be our upper. Any questions there? Okay, so let's evaluate. So we're going to go from 0 to 2. We're going to integrate with respect to y first. So if we do that, we're going to get 4y minus x squared y minus 1/2 y squared. And we're going to evaluate that from 0 to 4 minus x squared. And we're going to integrate with respect to x. Okay. Again, the nice thing is that if we plug in 0, we get 0. Okay, so all we got to do is worry about the upper limit. So we're going to do the integral from 0 to 2. So if I plug in 4 minus x squared for y, for the first term, I'm going to end up with 16 minus 4x squared. And I'm going to have minus x squared times 4 minus x squared. Then minus 1/2 times 4 minus x squared squared dx. Okay, so now it's just the fun part of just cleaning this up before we integrate. Okay, so if I do that, I'm going to have this. I'm going to have the integral from 0 to 2. For the first part, I'm still going to have the 16 minus 4x squared. Okay. For the next piece, I'm going to multiply negative x squared through. So I'm going to end up with negative 4x squared plus x to the fourth. And then I'm going to have minus 1/2. The next piece, I'm going to square that. So if I square that, I'm going to have 16 minus 8x squared plus x to the fourth dx. Okay, so I'm going to combine like terms. So I'm going to end up with 16 minus 8, which is 8. I got negative 8x squared plus 4x squared, which is a negative 4x squared. And finally, I'm going to have 1x to the fourth minus 1/2 x to the fourth, which is a positive 1/2 x to the fourth dx. Okay, so let's integrate. We're going to end up with 8x minus 4/3 x cubed plus 1/10 x to the fifth, evaluated from 0 to 2. Again, nice thing is that at 0, if I plug that in, I'm going to get 0, so we can kind of ignore the lower limit. Okay, so if I plug in 2, I'm going to get 16 minus 32 thirds plus 32 tenths. And when we calculate this, we should end up with, and hopefully I didn't screw up my calculations, 128 over 15. Any questions? Any questions? Okay, so that concludes everything with dealing with double integrals over a general region. Okay. All right, so I'm going to do one more section, and the last section I'm going to deal with is dealing with the area by double integrals. Double integration. All right, so if we want to find area by using a double integral, okay, so that means the area A is equal to the double integral over the region dA. Okay. Now, the other thing that we can do is what we refer to as the average value. And the average value is 1 over the area of the region R times the double integral over the region of f dA. So the average value equals 1 over the area of the region. And you're going to do the double integral over the region and then the function times dA. All right, so what we're going to do is to take a look at some examples of how we're going to do area, and then I'm going to do an example of the average value. Okay. All right, our first example is this. So let's find the area of the region bounded by x is equal to 0, y is equal to 2x, and y is equal to 4. Okay. So in order to be able to set this up, it's the best thing to do is to draw the region. All right. So based on the information we have, we got x is equal to 0, which is the y-axis. Y is equal to 4. So we're going to go up 4 units and have this. And then y equals 2x is the line starting at 0, 0. If x is 1, we get 2. If x is 2, we get 4. So this is our region. So if I'm going to find the area is going to be the double integral. Now we got to figure out what variable do we want to do. Do we want to do x first or y first? And it doesn't really matter in this case. Okay, so suppose in this case that I want to do dy then dx. Okay, so if I'm doing from dy to dx, all right, so on the outside is going to be x. Okay, on the outside is going to be x. So as far as x is concerned, based on the graph, what will the x values be?
0 to 2.
Okay, so we're going to do 0 to 2 here. Now, for the y, okay, we got to keep in mind that on the y, what's happening is that we're following along the curve. Okay, so for the y, the lower y value is not going to be 0. The lower y value is going to be the function, so it's going to be 2x. Then the upper y value is going to be what?
4.
4. So we're going to integrate from 2x to 4. So one of the things you always want to keep in mind when you are trying to set when you're doing something like this, if they give you, when you graph the region, if they give you an upper bound of the region as like a horizontal line, and then the other piece is like a line going to it, then you want to go from the function to that line, whatever the value of that line is. And the same way works with if it's from side to side. You want to look at it the same way. Okay? So if we take a look at this, this is a setup for this. Now, if you decided that you want to do dx dy, you can do that. But just keep in mind that the way the limits of integration will change. But you will still get the exact same answer. Okay? So if we integrate this first in respect to y, we're going to get from 0 to 2 of y evaluated from 2x to 4 dx. So what we're going to end up with is the integral from 0 to 2 of 4 minus 2x. Then we're going to integrate in respect to dx. Any questions so far? Okay, so if we integrate, we're going to get 4x minus x squared, evaluate from 0 to 2. Okay, so if we evaluate at 2, we're going to get 8 minus 4 at 0 is 0. So we're going to end up with 4. Any questions? Okay. Now, yes, we could do the area of this with a single integral and it wouldn't be any problem. If we did it in terms of a single integral, and let me switch pages real quick. If we did it in terms of a single integral, we're going to do a vertical cut, so we're going to integrate in respect to x, and it's going to be top function minus the bottom. And then our limits of integration are going to be from 0 to 2. Okay? And we're going to get the same answer, right? But by double integral, you notice that this portion, if you look at the last problem, actually are the limits of integration. So you got 4x at the top, 2x at the bottom. Okay? Any questions? Okay. All right, let's look at the next example. All right, in our next example, we are finding the area of the region bounded by y equals the natural log of x. And the second one should be y equals 2 times the natural log of x. I don't know if I fixed that on the document or not. And then the other one is the line x is equal to e. Okay, and we're in quadrant 1. So again, if I want to do this particular problem, again, I want to draw the region so I can see what I'm dealing with here. Okay, so for this particular problem, both of these functions intersect at when x is 1. They're both 0. Right, and we're going to go over to e. So the first one is going to come up with a y value of 1. The second one will come up with a y value of 2. And this is your graph. So if we want to find the area, we're going to do the double integral. All right. Now, this right here kind of dictates what variable should be integrated first. Okay. So based on that, what variable should we integrate first? We should integrate in respect to y first. So we're going to do dy, then dx. Okay. Now, if you look at the graph, we have the values of x set up. So what's the lower x value and what's the upper x value?
1 to e.
1 to e. Okay. And then for y, we're basically just doing top minus bottom. So the bottom function is represented by what? Yes, ln of x. And the top is represented by what?
2 ln x.
2 ln of x. Okay. And this is what we have. Any questions? Okay, so if we integrate, we're going to have that a is equal to the integral from 1 to e. We're going to have y, and then we're going to evaluate that from natural log of x to 2 times the natural log of x dx. So really, what we have is the integral from 1 to e. We're going to do the top minus the bottom dx, or we're looking at the integral from 1 to e of the natural log of x dx. All right, so how do we integrate the natural log of x?
It's going to be 1 over x.
That's a derivative.
Oh, wait. Excuse.
So how do we integrate the natural log of x? Yes. It's going to be, and basically the way you came up with that is that you use integration by parts. So it is going to integrate to x times the natural log of x minus x. We're going to evaluate from 1 to e. Okay. So you let natural log of x be your u, your dv is dx. All right. So if we evaluate at e, we're going to end up with e minus, if we evaluate at 1, we're going to end up with 0 minus 1. Our answer is 1. All right. Any questions? Okay, so what we're going to do, we're going to stop here for today. Okay, I know I've still got 3 more examples to finish up in this section, and we'll do them after break. I'm ahead of schedule, so way ahead of schedule, so it's fine for me to stop at mid of this. Okay, so you need to make sure that you are working on the 2 sections of integration. So the dealing with the double integrals, over rectangles, and also the general region. Okay, so you need to be working on those homework assignments. Also, quiz 11 is available, and it's due April 6th. Okay. Remember, next week is spring break. So there will be no classes next week. Okay. So hopefully this will give you guys some time to relax a little bit and also catch up if you are behind on things. Any questions? All right, guys, you have a great day. Have a great weekend. Have a restful next week and safe. And I'll see you guys again on the 6th. You're welcome. I plan to get some rest.